Lesson 11.4, Total Internal Reflection. Total internal reflection is when light hits an interface between two types of media with different indices of refraction, and it's all reflected back inside. Usually, some of the light is reflected and some is refracted. But there's a critical angle, and where the angle of incidence, where the refracted angle is 90 degrees. So, for example, down here, the light's coming in and it hits, but the refracted angle is 90 degrees, so it's right along the surface. If our angle of incidence is any more than that, then the refraction would be more than 90 degrees and be back into the medium. Well, that doesn't happen, so it just doesn't refract at all, and is all reflected. Angles of incidence larger than this critical angle cause the refracted angle to be inside the material. This can't happen, so no refraction occurs. So, to find our critical angle, well, we're going to use Snell's law, but we're going to say our angle 2 is 90 degrees. So use Snell's law, plug in 90 degrees. Oh wait, sine of 90 degrees is 1. So I divide by n1 and then take an inverse sine. So our critical angle is the inverse sine of n2 over n1. Alright, this will only occur if n2 is less than n1. So n1 has to be greater than n2, n2 has to be less than n1. Otherwise, it is not possible. So this is like having light shine from inside glass to the air. So a way you can do this is you can take a laser and shine it inside a chunk of glass and then watch it reflect off the inside piece of the glass as it's next to the air. So this would be like glass here and air here. If we had lab, we'd do this with a semicircular prism. We'd shine light in, and we would go and tell refracted right there, and we could measure that, and that would be our critical angle. What is the critical angle for cubic zirconia? N equals 2.16 to air. And then will the angle of incidence at 25 degrees produce total internal reflection? So let's start by finding our critical angle. Inverse sine of n2 over n1. Well, we're going from cubic zirconia to air, so n1 is the cubic zirconia and n2 is air. So this is our zirconia, and the top is our air. Run it through the calculator and you get 27.7 degrees approximately. So will 25 degrees produce total internal reflection? Well, is that more than the 27.7? No, it's less. So it will not produce total internal reflection. There are places where we use total internal reflection. Fiber optics is one case. You can use fiber optics on endoscopes or telecommunications. It's like we have this tube and the light comes along and hits it and bounces and hits and bounces its way along. So as long as it's total internal reflection, we will have, all the light will stay inside the tube and we won't lose any. Also decorations, like the Christmas tree. Binoculars and telescopes, they use a prism instead of a mirror. Makes them shorter. Reflectors, those little plastic reflectors. Gemstones, that's what gives it all the sparkle. We have the light reflecting around inside the gemstone, lots of total internal reflection, and it only comes out in certain areas. So light only comes at certain places and makes it sparkle. Dispersion is what happens if we shine more than one color. Each wavelength of light has a different index of refraction. It's close, but slightly different. The red is the lowest index of refraction, and the violet is the highest index of refraction. When the light is refracted, the violet bends more than red, and then that splits the colors. A rainbow is a dispersion with internal reflection. So what happens is our sunlight comes in and hits our water droplet. The red is bent more, so it goes over here. The violet is goes over here, bounces with internal reflection there. The red comes here and bounces over there. Because of the difference in indices of refraction, one color is bent more than the other, and it's split into the rainbow. Then it's reflected off the backs of the droplets. If you have a bunch of droplets in the air, off this top droplet, the person only sees the red because the violet reflected over their head. Off the bottom droplet, they only see the violet because the red's reflecting towards their feet. If you do that over a lot, you see all the entire rainbow. So if you want to see a rainbow when it's raining, look the opposite direction of the sun and you will see a rainbow. That means the sun is behind us when we're looking at this. The end of the flood. God told Noah, I set my rainbow in the clouds. It will be a sign of the covenant between me and the earth, that it will never again destroy the whole earth with a flood. Have a good day.